The talk is about the unification of physics, and the objective of unification is to resolve the conflict between quantum mechanics and general relativity, and to find a single theory of everything equation. Now, lots of people have tried to do this by starting with quantum mechanics and then trying to extend the mathematical equations to the very large scale. And this has met with mixed success. So the approach taken here is to start with general relativity as a complete description of space-time and try to apply these equations, the equations of general relativity, down at the very small scale. And it's always been problematical to develop theories of the structure of the atom because you can't actually see in detail what's going on. All you can do is form conjectures and make a guess at what the underlying structure really is, and then see if that develops into a worthwhile theory. So that's the approach. So we start from the point of view of general relativity, and the first question we have to answer is about the nature of light. So you may have seen in the news over the last couple of years an experiment called LIGO, which is a number of detectors. So there's 2 in the USA which detect gravitational waves. And these have detected gravitational waves, first of all, coming from the merger of black holes, and subsequently from the merger of neutron stars. And the interesting point about these observations is that with a neutron star merger, they've been able to detect the gravitational waves and also electromagnetic waves, for example, gamma rays and subsequently light rays. And what they found is that the waves arrive together. And remembering that these waves have come over a distance of, in this case, 130 million light years, that means that the waves have come through expanding space, which has been expanding at about 1% of the speed of light. So you may at first think it's not surprising that these waves arrive together, because 100 years ago, when they wrote down the equations of general relativity, they showed that gravitational waves would travel at the speed of light. But the important point to make is that current theories suggest that light travels as a wave of the electromagnetic field. In other words, that the field has a real physical existence and is the medium for transport of the light wave. And the electromagnetic field is independent of space-time. So what this result shows is that this couldn't be the case. That because gravitational waves and light waves arrive at exactly the same time, this must mean that they must have the same medium of transport. And so this reveals that light is actually a wave disturbance of space-time through space. So when we look at light being a wave disturbance of space-time, and we look at how light is emitted, in this illustration on slide 2, you can see depicted a hydrogen atom. And the red circle in the middle represents the nucleus, which is a proton. and the outer circles represent two possible positions of the electron. And when light is emitted by a hydrogen atom, it's emitted in very characteristic frequencies. And it's known that there are specific electron energies which result in the emission of particular frequencies of light. And the fundamental equation for this is the energy is equal to Planck's constant times the frequency. So when the frequency moves from F1 to F2, the light emitted is Planck's constant times F1 minus F2. This tells us two things. One is that light is quantized because that's the way it's emitted. And secondly, it shows that the electron itself must be a looped wave in space-time. So being a looped wave in space-time, it has the ability to emit a non-looped wave, which is the light wave. So where do electrons come from? Well, electrons come from the decay of a neutron. So this shows the decay process. A neutron, a single neutron on its own, which is not bound in a nucleus, would decay to a proton and an electron in a mean time of just under 15 minutes. And what this tells us is that both the neutron and the proton are looped waves in space-time. So thinking of the neutron, we can actually try to work out how many wavelengths there are in the loop. So for the proton, we know the mass of a proton. And using E equals mc squared, we can work out the energy of the proton. And using E equals hf, where h is Planck's constant, we can work out the frequency. And the frequency directly gives us the wavelength, because the frequency times the wavelength is equal to the speed of light. So now we've got a characteristic wavelength for the proton, and we know from the charge radius the approximate size of the proton, and from that it turns out that the proton must be around 3 wavelengths, because you just multiply x by the number of wavelengths, x by the wavelength, and put that equal to 2 pi r, where r is your effective radius, and that gives you a figure that x, which must be an integer, is going to be 3. And this is a very, very good result. When I got this result in the first instance, I was very positive, because if the result had come out that it was less than 1, or if it was 342, then that would have been discouraging. But given that it's 3, you can see that this is very likely to be a stable state. So now we've discovered that matter is made up of looped waves in space-time. So all matter is comprised of neutrons, protons, and electrons. And we can see that with this matter, the effect of those little curved looped waves in space-time at a distance will be to curve space-time at a distance. So where general relativity tells us that mass curves space-time, The space-time wave theory, which is what we're talking about, shows us how it does it. And then when you look at these looped waves in space-time relative to a gravitational field, so I've shown the Earth's surface here, which implies a gravitational field, you can think of these looped waves in space-time as a kind of gravitational field detector. So as these loops travel in the loop at the speed of light, the effect is for it to prefer to move to a lower energy state, and this results in an acceleration towards the Earth's surface, which we feel as the gravitational force. So the net result is that through the combination of the theory of general relativity and the space-time wave theory, we have fully defined the property mass, and we no longer require the idea of a Higgs field to give mass to particles. Now this experiment, the dual slit experiment, is a very revealing experiment in the sense that it is a good experiment to look at and describe in the context of any fundamental theory of the very small. So for example, the Copenhagen interpretation of quantum theory and the many worlds interpretation of quantum theory can describe how this experiment operates, and it gives you a good indication of the real true meaning of the theory. So I'm going to describe this experiment in the context of the space-time wave theory. And here we see a single photon is emitted from the light source. It passes through both slits, and so you get wave interference. And the photon wave arrives in the vicinity of the detector screen. So this detector screen could be a photographic paper. And at the point of detection, a single electron on the detector screen will absorb the entire photon wave. So it's not as if we've got some mysterious collapse of a wave function. What we're talking about is a real physical wave, but that real physical wave, which is the photon, interacts with the outer electron of an atomic shell on the detector screen, and you can think of the electron as absorbing the entire photon wave, even though it might be spread out over several centimeters. And this is a very important distinction, and this is referred to as the active role of the detector in the operation. And this description completely resolves the measurement problem, which is a famous problem of quantum mechanics, which has been sitting on the table for 10 or 20 years or more. So it's useful to compare the Copenhagen interpretation with the space-time wave theory description of the electron. And in the Copenhagen interpretation, it would say that there's a point particle with mass m and momentum p, and that exists with a probability distribution around the nucleus. Now, if you then think of the looped wave of the electron as being the track of this particle, then what you find is that the momentum is actually spread out over the entire length of the wave, and this electron wave is looping itself many times around the nucleus. But this equivalence means that we can adopt the very important equation of quantum mechanics, which is the Schrödinger equation, which is a very high degree of predictive value in terms of the very small. So what we're doing is using the Schrödinger equation, but we're substituting a different physical description underneath that equation. So this is the question of electric charge. And prior to this theory, electric charge has just been considered to be a fundamental property. So an electron has one negative charge, and in the standard model of particle physics, the quarks would have minus a third and plus 2/3 of electric charge. But this, what this slide is showing is the fundamental nature of electric charge by looking at the space-time wave. Now, so far we've been talking about gravitational waves, which you can think of as a moving compression and expansion of space, propagating through space. So what would happen if we had a wave variation in the time dimension, as well as a wave variation in the space dimension? So remember, we're talking about space-time, and the effect is that you can see that the period that space is expanded and the period of space compression is no longer the same. So when you get a wave variation in the time dimension, what happens is that you get a net expansion of space or a net compression of space. And what this means, it comes back down to a question of energy. So if you think of two electrons, and they both have a net expansion or a net compression of space, and so by moving them apart, they move to a lower energy state. What I can't tell you is whether it's expansion or compression that corresponds to the positive or negative. That's something that will have to be discovered, but it does provide a space-time explanation for electric charge, which is really important. So now we look at the subject of electron spin. And this is something which, if you look in the publications, it's a kind of mysterious property which is very hard to explain in current quantum theory, because somehow you have this point particle with a probability distribution which has a spin. But when you think of the electron as a looped wave, then it all becomes clear, because let me just explain what the experiment does. Is they heat silver atoms and they pass them through a magnetic field, and what's observed is that the beam splits. So you get hits on the detector screen above or below the midpoint, but not in the middle. And the explanation for this is that the silver atom is a particular case where you've got a number of shells, and then you've got one electron in the outermost shell. And that electron can be randomly oriented around the nucleus plus the inner shells. But at the point at which it's passed through the magnetic field, it can only adopt one of two possible orientations, illustrated on the right-hand side, which is clockwise or anti-clockwise. And because of that, it forms a magnetic dipole, and this will cause the atom to move up or down as revealed by the experiment. So this is a much better explanation of electron spin, and it also is a better explanation than trying to give spin some mysterious quantum properties where you say, well, it's a superposition of spin up and spin down, which actually doesn't really make a lot of sense. So this equation is the theory of everything equation, the core theory equation. And it looks a bit complicated, and some of you might recognize it, but it's the Einstein equations of general relativity without the cosmological term. So on the left-hand side of the equation, it is describing the curvature of space-time, and the right-hand side of the equation, the T mu nu, is the mass energy distribution. And this equation, or derivatives of it, have been used to model black holes and neutron star mergers and the passage of light around the sun and the change of the orbit of Mercury. So it works very, very well at the large scale. And so what I'm saying is that the neutron that was depicted in the bottom half of the picture here is a looped wave in space-time of 3 wavelengths. And so it's entirely appropriate that we should try to model this looped wave in space-time using this core theory equation. So I have to say, I haven't done it yet. When it comes to applying the Einstein equations, even when they're applying it to black hole mergers and neutron star mergers, they can't, the best way they can proceed is by having a guess at an initial state and then looking at the incremental changes. So the same kind of approach would be used to apply this equation to the very small. But what you can see is that this equation, this core theory equation, has the potential to be the theory of everything equation, simply because all matter is comprised of looped waves in space-time. So this is a slightly different depiction of the neutron. So you remember we talked about electric charge as being successive expansion and compression of space. So with the neutron, we've got 3 wavelengths, and we can depict that as 3 positive and 3 negative charges in succession. And the wave in the loop is traveling at the speed of light, c. So you can see from this diagram that if you had 2 neutrons which were sharing the same spin axis and they found themselves in close proximity, they would bind very tightly, positive to negative. And this is the proposed dark matter particle, which everyone's been looking for. So finally, this is the last slide of the presentation. And no talk on unification would be complete without looking at the fundamental forces of nature. And the message from this slide is that forces themselves are not fundamental. So we've known for some time that the force of gravity is not really a force. It's simply an effect of curved space-time resulting in objects in space-time being accelerated due to the energy difference with possible positions. And you can look at each of the fundamental forces. It's usually termed that there are four, but I've separated out the electromagnetic force into electrostatic and magnetic. And you can look at each of them in turn in terms of the space-time wave theory and see that indeed the cause of the force is simply an energy difference between possible positions of objects in space-time. And so the type of force depends on the context in which it occurs. So what this means is that we devised a scheme where everything reduces to space-time. So we've explained mass in terms of space-time. We've explained electric charge in terms of space-time. Then a force, we've explained in terms of an energy difference, which is related to space-time. And finally, a field, we actually go back to the classical idea of a field, which is a three-dimensional map of force vectors. And the idea of a quantum field being fundamental in some way is replaced by this theory. So that concludes the presentation. I will try, I've lost my mouse, so I'm going to try and take us off sharing. I'll take it one step further, and there we go. So has anyone got any comments or questions on the presentation?